Good morning, everyone. Today we will discuss the chapter Mechanism of the Reaction of BSc First Year Chemistry Honors of Modern Published Yearbook. Mechanism of Organic Reactions. Introduction. During the study of organic chemistry, we come across numerous reactions which the organic compounds undergo. As we study these reactions, we can not only want to know which reactant gives rise to which product, but we also interested in knowing how it happens. Do the reactants change directly into products in a single step, or does the reaction take place by several steps through the formation of reaction intermediates? The complete description of how a particular reaction takes place is called mechanism of the reaction. It tells us which bond can broken and in what order, and which bond are formed and in what order. It also tells what kind of intermediates are involved and what are the relative rate of different steps. We shall now consider some important notation and basic concept involving the study of organic reaction and their mechanisms. Important notations. Reaction of organic compounds involve the breaking and making of covalent bonds and the movement of electrons from one side to another. To indicate these changes, certain notation involving the use of different kind of arrows have been adopted as described below. Curved arrow notation. It is very useful notation in which a curved arrow indicates the movement of electron as bond in reactant are broken and new bonds in product are formed. It means that an electron pair moves from the atom at the tail of the arrow to the atom at which head of the arrow. This is illustrated below with the help of reaction between water and hydrogen chloride. The electron pair moves from oxygen to hydrogen. The bond between hydrogen and chlorine breaks and electron pair moves to chlorine. The electron pair that moved from oxygen form a new bond with hydrogen to get hydronium ion. The electron pair of HCl bond goes to Cl to form Cl negative ion. Similarly, reaction between acetylene and amide ion to form acetylide ion as ammonia may be shown as follows. Half-headed arrow. As will be described in section 2.3, sometimes a bond between two atoms breaks in such a manner that each atom gets one electron of the shared pair. To represent this type of symmetrical bond breaking and bond making, half-headed arrow are used as shown ahead. It may be noted that a half-headed arrow is used for showing the movement of a single electron, while a full-headed arrow is used for a pair of electrons. Double-headed arrow. This is a type of arrow are placed in between the various canonical structures or resonance structures of a substance, which exhibit resonance. This is to indicate that the actual structure is a hybrid of these structures, which are hypothetically and not real. These are only imaginary structures. For example, double-headed arrow are placed between the two major canonical structures of benzene to indicate that the actual structure of benzene lie between these two structures, which do not have real existence. Types of bond cleavage. Reaction of organic compounds almost invariably take place through the breaking and formation of covalent bonds. Depending upon the nature of a given compound, the nature of attacking reagent and the reaction condition, a bond between two atoms of a molecule may be cleavaged or broken in different ways, producing different type of reaction intermediates. The different possibilities are illustrated below by considering a covalent bond between two atoms A and B. Homolytic cleavage or homolytic fission or homolysis. This involves the breaking of a covalent bond in such a way that each atom separates with one electron of shared pair. This leads to the formation of highly reactive neutral particle containing odd or unpaired electron and known as free radicals. It may be seen that the homolytic cleavage of bonds is shown by using half-headed arrows in pairs. Heterolytic cleavage or heterolytic fission or heterolysis. This involves the breaking of bonds in such a way that both the electrons of shared pair are carried away by one electron, one of the atom. Heterolytic fission leads to the formation of charged or ionic species, one having a positive charge and other having a negative charge. If both the shared electrons are taken away by A, it would be converted into an anion and B into a cation. On the other hand, if both the shared electrons are retained by B, it would change into an anion, while A would form a cation as shown above. Quite often, the ionic species formed by heterolytic fission bear the positive or negative charge on carbon. Such ionic species are known as carbocations or carbanions. According to carbon carries positive or negative charge. It may be mentioned that if a particular covalent bond can undergo either homolytic cleavage or heterolytic cleavage under different conditions, the bond dissociation energy for homolytic cleavage is considerably different from that of heterolytic cleavage. In general, the value of homolysis are low while they are quite high for heterolysis. For example, bond dissociation energy of carbon chlorine bond in methyl chloride for homolytic and heterolytic cleavage are 351 and 949 kJ per mole respectively. Reaction intermediates. The student is already familiar with the fact that in organic reaction, the starting substance seldom change into the product directly in one step. On the other hand, the reactants first change into intermediate substance called reaction intermediates, which ultimately yield the product. The reaction intermediates are generally very unstable and reactive substances which cannot be even isolated. We now briefly deal with the main reaction intermediates which we often come across in organic chemistry. Carbocations. What are carbocations? A carbocation is a cation in which the positive charge is carried by a carbon which has only 6 electrons in its valence shell. For example, methyl carbocation and ethyl carbocation are simply carbocations known as methyl cation and ethyl cation, respectively. A carbocation may be assumed to be fragment of molecule from which an atom or group singly bound to a carbon gets removal along with the pair of bonding electrons. For example, if a bromide ion is removed from a molecule of tert-butyl bromide, tert-butyl cation would be formed as shown below. Carbocations are very short-lived and high reactive species. The reactivity of carbocations is due to their tendency to complete the octet of electron deficient carbon. As a result, carbocations undergo a variety of reactions. Formation of carbocations. Carbocations can be generated in many different ways. Some of the reactions in which they are formed given below. Direct ionization. The carbon halogen bond in many organic halides generates carbocation in presence of highly polar medium. For example, tert-butyl chloride gives tert-butyl cation by the protonation of unsaturated compounds. Unsaturated compounds such as alkenes, carbonyl compounds, and nitrile furnish carbocations on treatment with proton donating solvents. For example, from compounds containing an atom with lone pair of electrons. When an organic compound having one lone pair of electrons on an atom is treated with an acid, protonation of this atom take place. This is followed by the elimination of simple molecule containing this atom to furnish a carbocation. Alcohol gives protonated alcohol gives carbocation by the decomposition of diazonium salts. For example, primary amine gives diazonium cation gives carbocation by action of superacid on alkyl fluorides. For example, RF plus में SbF5 gives R positive alkyl cation. The term superacid is used for some exceptional strong acids such as SbF5 plus MeHF or SbF5 plus MeFSO3H dissolved in SO2 or SO2CIF. CLF. Structure of carbocations. Positive charged carbon of the carbocation in sp2 state of hybridization. The three sp2 hybrid orbitals which lie in same plane are involved in the formation of three bonds with other atoms. The unhybridized p orbital remain vacant. Thus, the carbocation has a flat structure as represented on the right hand side. The bond angle around the positively charged carbon atom is nearly 120 degree. Classification of carbocation and their order of stability. Carbocations are classified as primary, secondary or tertiary according to the carbon bearing the positive charge is primary, secondary or tertiary in nature. In addition, methyl ion having only one carbon is regarded as a special case. Methyl cation, ethyl cation, isopropyl cation, tert butyl cation. Explanation of relative stabilities of alkyl carbocations. A basic principle involved in discussing the relative stabilities of carbocation is that how does a given factor influence the magnitude of positive charge carried by the electron deficient carbon of carbocation. It is apparent that any factor which tends to disperse the positive charge by distributing it over the rest of molecules stabilize the carbocation. In contrast, any factor which tends to intensify the positive charge destabilize the carbocation. The relative stabilities of alkyl carbocation as given above can explain in terms of inductive effect and hyperconjugation in terms of above principle. Inductive effect. This is the main factor operating in determining the relative stabilities of carbocations. As is well known, the alkyl group are more electron releasing than hydrogen. As such, alkyl group attached to positive charged carbon of carbocation tend to release electrons toward the carbon due to plus I effect. In this way, the positive charge on carbon get dispersed. The dispersal of the charge stabilizes the carbocation. Now, the more the number of alkyl groups, greater the dispersal of positive charge, and therefore more the stability of carbocation. That is why tertiary carbocation having three alkyl groups attached to the positive carbon is more stable than a secondary carbocation with two alkyl groups. The secondary ion in turn is more stable than a primary carbocation having only one alkyl group. The methyl carbocation does not have any alkyl group as is therefore the least stable. Tertiary carbocation maximum dispersal of positive charge, maximum stability. Methyl carbocation least dispersal of positive charge, least stability. Hyperconjugation. The concept of hyperconjugation is also to some extent responsible for the observed order of relative stabilities of carbocations. Hyperconjugation can take place here through the overlap of sigma orbital of alpha carbon hydrogen bond of alkyl group and the empty p orbital of carbocation, taking C2H5 positive to represent a carbocation. In general, delocalization of electron through sigma p orbital overlap may as shown. In terms of resonance, the above situation may be depicted as the net result is that the actual structure carbon-hydrogen bond is slightly lesser than a single bond. The carbon-carbon bond has some double bond character while the positive charge is partially accommodated by hydrogen atom. This partially accommodation of positive charge over hydrogen leads to dispersal of charge and consequently destabilize the ion. In methyl carbocation, no such dispersal of charge is possible because hyperconjugation does not take place. In ethyl carbocation, primary carbocation which contain 3 alpha hydrogens, the positive charge can be dispersed over Three hyperconjugation structures possible in condition to normal structure as shown. In isopropyl carbocation, which contains 6 alpha hydrogen, there are 6 hyperconjugation structures are possible. In tert-butyl tertiary carbocation, which contains 9 alpha hydrogen, there will be 9 hyperconjugation structure possible. As number of contribution structure and with the dispersal of charge become more, stability of carbocation goes on increasing. Thus, the relative stability of alkyl cation may be due to a combination of inductive effect and hyperconjugation, although it is usually explained in terms of inductive effect alone. Conjugation of positive charge with a double bond or benzene ring. Resonance stabilization. The carbocations in which the positively charged carbon atom is conjugated with a double bond or benzene ring have been found to extra stability, thus has been attributed to resonance effect involving the electrons of double bond. For instance, allyl cation is a resonance hybrid of two equivalent structures as shown below. It is apparent that positive charge on carbon of carbocation get dispersed over two carbon atoms. Hence, the alkyl cation acquires greater stability and is found to be more stable than simple alkyl cations. Similarly, benzyl carbocation is greatly stabilized by resonance as shown below. It is evident that carbocations having more than one phenyl group attached to positive charged carbon would be still more stable. This is because there will be greater dispersal of positive charge due to large number of contributing structures. Accordingly, diphenyl methyl carbocation would be more stable than benzyl carbocation. In fact, triphenyl methyl carbocation is so stable that some of its salts, such as perchlorates, can be isolated and stored for months. Effect of substituents on the stability of benzyl carbocations. It can be readily understood that presence of electron releasing group at ortho and para positions of phenyl groups will tend to further stabilize the benzyl carbocation. On the other hand, the presence of electron withdrawing group at these positions would be opposite effect. For example, order of stability of following substituted benzyl ions are: instability of vinyl and phenyl carbocations. The carbocations in which positive charge is carried by doubly bond carbon atom, such as vinyl cation and phenyl cation, are found to be highly unstable. This is because these ions do not undergo resonance stabilization at all. The reason for lack of resonance is that vacant orbital of carbon carrying the positive charge is perpendicular to double bond, and therefore it cannot participate in resonance. Determination of relative stabilities of different kinds of carbocations. It is evident from the above discussion that the stability of carbocation is primarily related to dispersal of charge carried by positive charged carbon. The dispersal of charge may due to inductive effect, hyperconjugation effect, or resonance effect, as explained above. The relative stability of different kinds of carbocations can be measured in terms of heterolytic bond dissociation energies leading to the formation of carbocation. On the basis of these values, the decreasing order of stabilities of some carbocation are given ahead. Rearrangement of carbocations 1 to shifts. An important feature of carbocations is that they can undergo rearrangement reaction to form more stable carbocations. These rearrangements involve the shift either a hydrogen or alkyl or aryl group along with its electron pair from an adjacent carbon to the positive charged carbon. Such shift known as 1 to shift. The shift of hydrogen is known as 1 to hydride shift, while of alkyl group is known as 1 to alkyl shift. The cation thus formed contain a new charge center and more stable than original carbocation. 1,2 shift. Propyl carbocation 1,2 hydride shift give isopropyl cation secondary more stable. N-propyl cation 1,2 methyl shift neopentyl carbocation primary 1,2 methyl shift gives 2-methyl 2-butyl carbocation tertiary more stable. Carbanions. What are carbanions? What are carbanions? A carbanion is an anion in which negative charge is carried by a carbon. This carbon has 3 bonds with one or more than atoms and possesses a lone pair of electrons. For example, methylene is a simple carbanion known as acetylide ion. A carbanion may be assumed to be a fragment of molecule when one of the atom or groups singly bound to a carbon is removed without the bonding pair of electrons. For instance, removal of a hydrogen of methyl part of acetaldehyde molecule as a hydrogen ion result in formation of carbanion as shown below. Carbanions constitute highly unstable and one of most reactive reaction intermediate in organic chemistry. They are very frequently involved in the reaction of aldehyde ketone, ester, etc. Their reactivity is due to fact that negative charge carbon in turn has got a lone pair of electrons. It has a strong tendency to donate this pair to some electron deficient species. Therefore, carbanions easily participate in many reactions. Formation of carbanions. First, by the dissociation of molecule in which an atom or group singly attached to carbon leaves it without the electron pair, that is, in most of cases the leaving group is proton and hence base is required to facilitate the process. Thus the formation of carbanion is an acid-base reaction. Since the presence of electron attracting substituents such as carbonyl, cyano, nitro groups on carbon carrying hydrogen makes the hydrogen relatively more acidic, the generation of carbanions from such compounds plays a very important role in organic reactions. For example, to remove a proton from a hydrocarbon, very strong base such as sodamide in liquid ammonia has to be used. The aromatic compounds of this type of triphenylmethane generates carbanion very easily in the presence of base. It may be pointed out that apart from protons, other leaving groups are also known to lead the formation of carbanions. For example, by the addition of a nucleophile to carbon-carbon multiple bond. By this type of addition occur only when the double bond is activated towards nucleophilic attack of electron withdrawing groups such as carbonyl, cyano and nitro groups. Structure of carbanions. The negatively charged carbon of carbanion is the state of sp3 hybridization, so that hybridized orbitals are directed towards the corner of a tetrahedron. These 3 of hybrid orbitals are involved in formation of single bonds with other atoms, while the 4th orbital contains a lone pair of electrons. Thus, carbanion has distorted tetrahedral or pyramidal structure, such as shown on the right hand side. Both the bond angles around negatively charged carbon are less than 109 degree 28 minutes. This is because bond pair repulsion is greater than bond pair repulsion. Free radicals. What are free radicals? A free radical is an atom or group of atoms having an odd or unpaired electron. It is denoted by putting a dot against the symbol of atom or group of atoms. For example, chlorine free radical stands for a chlorine free radical, while methyl dot denote a methyl free radical. Free radical are electrically neutral species which are usually formed by the homolytic cleavage of molecule in reactions taking place in gas phase or in non-polar solvents. Due to presence of all electron, free radical are paramagnetic in nature. Free radicals are highly short-lived species. They are extremely reactive and soon as they are formed, they intermediate participate in some further reactions. Their greater reactivity is due to the tendency of the odd electron in turn to get paired up. Formation of free radicals. There are two main methods by which free radicals are usually formed: by thermal or photoelectric, a photochemical homolysis of a covalent bond. For example, tetramethyl lead on heating gives lead plus 4 methyl free radicals. Benzoyl peroxides on heating give benzoyloxy free radicals, gives phenyl free radical plus carbon dioxide. Structure of free radical. It may be pointed out that in case of free radicals containing carbon, the state of hybridization of carbon atom having odd electron is not clearly established. However, there is strong evidence to indicate that most of alkyl free radicals such as methyl radical are actually planar. This means that the carbon atom carrying the odd electron is in sp2 hybridized state. The three coplanar hybrid orbitals are involved in the formation of three single bonds with other atoms. The unhybridized p orbital, which lie in a plane at right angle to the plane of hybrid orbitals, carries the odd electron. The bond angle around the carbon carrying the odd electron is approximately 120 degree. Classification of free radicals and their order of stability. Alkyl free radicals are classified as primary, secondary, and tertiary according to the odd electron is carried by a primary, secondary, or tertiary carbon atom. Bimethyl free radical CH3 having only one carbon is treated as a special case. We have methyl free radical, ethyl free radical, isopropyl free radical, and tert-butyl free radical. The order of stability of different type of free radical relative to alkane from which they are derived to be found: tertiary, then secondary, then primary, then methyl. This order is derived from the bond dissociation energy involved in the formation. The lesser the bond dissociation energy in the formation of free radical, more its stability. To illustrate the above statement, let us consider the homolytic fission of alkane into a alkyl radical and a hydrogen atom. That is, it is apparent that del H of such a dissociation process must equal to bond dissociation energy of bond between the concerned hydrogen and carbon of alkyl group. A study of del H of several reactions involving the dissociation of different alkanes to form different classes of alkyl radicals showed the amount of energy required to form various classes of alkyl radicals in order: methyl, then primary, then secondary, then tertiary. If more energy required to form one radical than other, it means that relative to the alkane from which it is found, the radical to contain more energy than the other and hence less stable. This concluded that relative to the parent alkane in such order of stability of free radical is tertiary, then secondary, then primary, then methyl. It must be emphasized that this order is based on the differences in between energy alkyl radical and parent alkane in each case. As such, it does not reflect the order of absolute stabilities of individual radicals. Let us consider the case of methyl radical and ethyl radical, which is simple primary radicals. The difference in energy between methane and methyl radical is more than difference in between ethane and ethyl radical. This merely means that stability of methyl radical relative to methane is lesser than stability of ethyl radical relative to ethane. Explanation of relative stabilities of alkyl free radicals. Hyperconjugation. The relative stabilities of alkyl free radical are explained primarily in terms of concept of hyperconjugation with the exception of methyl free radical. All the other alkyl free radicals undergo hyperconjugation through overlap between sigma bond of alkyl group and a p orbital containing the odd electron. As a result of this overlap, the dissociation electron help in binding together three atoms, two carbon and one nitrogen to some extent. In terms of resonance, the above situation may represent by saying that given alkyl free radical is resonance hybrid, two contributing structures are shown below. Comparison of singlet and triplet carbene. Singlet carbene. In this, two unsaid electrons are present as pair in one orbital. Triplet carbene. In this, the two unsaid electrons are present at two unpaired electrons in different orbitals, and thus it represents a biradical. It is relatively less stable. Triplet carbene is relatively more stable. Singlet carbene, the central carbon atom is sp2 hybridized. In triplet carbene, central carbon atom is sp hybridized. Nature of reagents. When two substances react together, one of the substances is regarded as the attacking reagent while the other is taken as a substrate. The new substance formed as a result of reaction are called products. Thus, the occurrence of chemical reaction may be depicted as substrate plus attacking reagent gives products. It may be pointed out that the term attacking reagent is usually employed for substance whose presence brings about a chemical change in given substance to form the products. But the use of the two terms is purely relative. A particular substance may be termed as a substrate in one reaction and an attacking reagent in the other. However, the following conventions are generally followed in the use of two terms. In a reaction between an organic and inorganic substance, the organic substance is treated as substrate while the inorganic substance is taken as attacking reagent. Example, iodoethane substrate plus aqueous KOH attacking reagents give ethanol plus Ki. In a reaction between two organic substances, the substance which supplies the carbon atom in the formation of new bond between carbon atom and hetero atom is treated as the substrate. The other substance is taken as attacking reagent. Ethanoic acid substrate plus methanol attacking reagents gives classification of reagents. There are three types of attacking reagent taking part in organic reactions. These are free radicals. Their formation and reactivity has already been discussed. Electrophilic reagents. An electrophilic reagents or an electrophiles electron-loving species is a reagent containing an atom which is deficient in electrons. Because of the presence of electron deficient atoms, such as reagent tries to seek electrons from other sources and thus behave as a Lewis acid. It attacks a molecule at the point of high electron density. Types of electrophiles: positive charged ions or positive electrophiles. These are electrophiles reagents in which the electron deficient atom does not carry any charge. For example, AlCl3, FeCl3, BF3 belong to this category. There are certain substances in which the central atom has a complete octet of electrons and still it has a tendency to coordinate more electrons due to presence of empty d orbitals. SnCl4 affords an example of such an electrophile. Carbenes also act as electrophiles because the carbon in them has only 6 electrons rather than an octet. Reactions involving electrophilic reagents are known as electrophilic reactions. Nucleophilic reagents and nucleophilic reagent or a nucleophile nucleus-loving species is a reagent containing an atom having an unsaid or lone pair of valence electrons. Because of this free pair of electrons, such as reagent is in search of site with which to share electrons, and in this way behaves as a base. Lewis concept of bases. It attacks a molecule at a point of low electron density. For example, consider AOH negative ion. The oxygen present on ion contains unshared pair of electrons due to the reason OH negative ion attack any molecule containing a center of low density, so to share the electrons at the point. Type of nucleophiles. Nucleophiles are of two types: negative nucleophiles or negative charged ions. All negative charged ions such as hydroxyl ions, OH negative halide ion, X negative alkoxide ions, RO negative cyanide ions, Cn negative and carbon ions act as nucleophilic reagents. Neutral nucleophiles. These are nucleophiles reagent which contain atom or lone pair of electrons but not carry any charge. Water H2O, ammonia NH3 and alcohol ROH are neutral nucleophiles. Classification of organic reactions. The organic reactions may be broadly classified into the following categories. These are substitution or displacement reactions, addition reactions, elimination reactions, rearrangement reactions, isomerisms reactions, condensation reaction, molecular reactions. First, as substitution reactions. A substitution reaction is that which involves the direct replacement of hydrogen atom or some other group of molecule by some other atom or group without any change in structure of the remaining part of the molecule. The product obtained is known as substitution product, and new atom or group which enters the molecule is known as substituent. For example, when chloride reacts with methane in presence of diffused sunlight, the hydrogen atoms are replaced by chlorine atoms one after other, leading to formation of substitution products. Methane plus में chlorine, methyl chloride plus में HCl. Similarly, the reaction of methyl iodide with an aqueous solution of potassium hydroxide to form methyl alcohol is a substitution reaction. Methyl iodide plus में aqueous KOH gives methyl alcohol plus में potassium iodide. Substitution reaction may involve free radical, electrophilic or nucleophilic reagents. According, they are subdivided as: first, free radical substitution reactions. For example, hydrogenation of alkane is a free radical substitution reaction. Electrophilic substitution reaction. Nitration and sulfonation of benzene are important example of electrophilic substitution reaction. Benzene plus में nitronium ions gives nitrobenzene. H positive ion removed by a base. Nucleophilic substitution reactions. Substitution reactions of alkyl halides are nucleophilic substitution reactions. OH negative ion plus में methyl iodide gives methanol plus में iodide ion. I negative. Addition reactions. An addition reaction involves the combination between the molecules of two reacting substances to form a single compound known as addition product. One of the reactants is in such reactions always contains double or triple bond in a molecule. For example, ethylene plus में bromine gives ethylene dibromide. Addition reaction may also involve free radical, electrophilic or nucleophilic reagents. As such, they subdivided as: free radical addition reaction. Addition of HBr to alkene in presence of benzoyl peroxide is well known example of free radical addition. Propene plus में hydrogen bromides on benzoyl peroxide gives N-propyl bromide. Electrophilic addition reactions. Most of addition reactions of alkenes are electrophilic addition reactions. Nucleophilic addition reactions. Aldehyde and ketones undergo nucleophilic addition reactions. Acetaldehyde on H positive gives acetaldehyde cyanohydrin. Elimination reactions. These reactions involve the loss of atom or groups of atoms from a molecule to form compounds containing double or triple bonds. Thus, these reactions are essential in the reverse of addition reactions. The common reaction of this type involve the elimination of atoms or groups from adjacent carbon atom to yield alkenes. For example, propyl chloride plus में alcoholic KOH gives propylene plus में H2O. Unimolecular elimination reaction. Are elimination reactions in which rate determining step involve only one molecule. For example, dehydrohalogenation of tertiary alkyl halide usually proceeds by even mechanism. Tert butyl chloride plus alcoholic KOH gives 2-methyl propene plus KCl plus water. Biomolecular elimination E2 reactions. These are elimination reactions in which rate determining step involves two molecules. For example, primary alkyl halide such as N-propyl chloride shown above generally undergo dehydrohalogenation by E2 mechanism. Depending upon the relative position of atoms or groups eliminated, these are also classified alpha, beta or gamma elimination reactions. Alpha elimination reactions. These are reactions in which loss of two atoms or groups occurs from the same carbon atom of the substance. For example, chloroform gives dichlorocarbene plus water plus chloride ion. Beta elimination reaction. In these reactions, loss of two atoms or groups occurs from adjacent atom of substance. For example, ethanols on concentrated H2SO4 or heating gives ethene plus water. Gamma elimination reactions. In these reactions, loss of two atoms or groups occur from alpha and gamma positions of a molecule, giving rise to formation of three-membered rings. 1,3-dibromopropane on zinc dust and heat gives cyclopropane plus zinc bromide. That is front reaction. Rearrangement reactions. These reactions involve either the migration of functional group from one atom to other or complete rearrangement of chain of carbon atoms present in compound to form a product. For example, 1-bromobutane on AlCl3 at 575 Kelvin temperature. 2-bromobutane N-butane on AlCl3 and HCl heat in a sealed tube gives 2-methylpropane. These arrangements also take place through the formation of electrophile, nucleophile or free radical intermediates. It is interesting to note that preparation of first organic compound, urea, to be synthesized in laboratory involve a rearrangement reaction. Ammonium cyanate on heating gives urea. Isomerism reaction. The reactions involving the conversion of one isomers to another so that molecular formula of carbon skeletons of reactant and products always remains the same. For example, conversion of trans to butene to cis to butane and vice versa is geometrical isomerism reaction. Trans to butene on heat on light on in presence of light gives cis to butene. Condensation reactions. These are reactions in which two or more molecules of same or different reactants combine to form product with the or without elimination of simple molecules such as water or alcohol. For example, when acetaldehyde is treated with dilute alkali, two molecules of acetaldehyde combines to form 3-hydroxyl-butanol. Reaction is called aldol condensation. Acetaldehyde two molecules plus में ethanol on dilute NaOH gives 3-hydroxybutanol or aldol. Molecular reactions. These are reactions in which involve recognition of covalent bonds either intramolecular or intermolecularly through cyclic transition state. under the influence of heat or light. The reactions do not require any catalyst or no ionic or free radical intermediate is involved. These are collectively called pericyclic reactions. Electrocyclic or cycloaddition reactions are typically examples of such reactions. Electro Electrocyclic reactions. These reactions involve conversion of an acyclic die into cyclic alkenes and vice versa. For example, buta 1,3 die on heating or light gives cyclic transition state, on further gives cyclobutane. Cycloaddition reaction. These reactions involve addition of two unsaturated molecules of same or different substance to form cyclic products. An example of this type is 4 plus 2 cycloaddition reaction given below. Energy changes during reactions. All chemical reactions involving the breaking and making of bonds, since energy is required to break a bond while energy is released in formation of a bond. The occurrence of chemical reactions is always accompanied by energy changes in one form to another. We will therefore now present briefly certain basic concepts regarding energy changes such as enthalpy of reaction, energy of activation or transition state. Heat or enthalpy of reaction. Heat or enthalpy of reaction del H is total energy change which comprises the conversion of a definite number of moles of the reactant into the product. It is possible to calculate the enthalpy of reaction on basis of bond dissociation energies of various bonds broken and formed during the reactions. Energy of activation theory, collision theory. An important feature of most of reactions, whether endothermic or exothermic, is that the reactants acquired some more extra energy for the reaction to take place. To understand the reason for this, let us recall that according to collision theory, the primary condition for a reaction to take place is that the reacting particles must come in contact or collide with each other. But all such collisions do not result in formation of product. In order to effective in bringing about the reaction, a collision should fulfill two conditions. The colliding particles must have a certain minimum amount of energy, known as threshold energy. The colliding particles must be properly oriented with respect to other at time of collision. As far as the energy factor is concerned, most of reactants molecules do not possess sufficient energy in their ground state for effective collision to take place. As a result, when such molecules collide with each other, no bond breaking or making take place, and the colliding particles bounce back as such. Therefore, extra energy is needed for reactant to form product. The minimum amount of additional energy required by the reactants to undergo effective collisions, known as activation energy, EA. It is numerically equal to difference between threshold energy and ground state energy of reactant. E activation equal to E threshold minus E ground state. Most of organic reactions have activation energy in range of 40 to 150 kilojoule. If the activation energy has a low value, reaction can take place at room temperature. On the other hand, reaction with high activation energy take place on heat. Gibbs free change. Gibbs free energy change del G is very useful parameter for determining the feasibility and direction of occurrence of a reaction. It is related to change of enthalpy and change in entropy. Entropy means randomness as follows: del G equal to del H minus T del S. We all the substances are in standard state. The relationship may be written as del G naught equal to del H naught minus T del S naught. The enthalpy term del H naught is directly related to bond strength in the starting substances and the products. The entropy term del S naught is a measure of change in amount of molecular randomness or disorder caused by the reaction. A reaction takes place in forward direction only if it have a negative value of G. Free energy of product is lesser than that of reactant. On other hand, a positive value of G means reaction has a tendency to take place in backward direction. In case of equilibrium reaction, equilibrium K constant K is related to del G naught as del G naught equal to minus 2.303 RT log K. Transition state theory. Energy diagram of a reaction. In transition state theory has been very useful in understanding the mechanism of organic reaction and the energy changes take place during the reaction. According to this theory, the reactant do not change directly to the products, but what happens is that when reactant molecules come in contact with each other, it leads to formation of highly unstable arrangement of atoms whose energy correspond to the energy barrier separated the reactants and the products. The high energy species thus formed is known as activated state or transition state. For example, in a single step reaction represented by the equation A plus B bond C, AB bond plus C. Transition state merely represented a probable arrangement of atoms corresponding to the energy barrier in which a bond is partially but not completely broken and a new bond has begun to form but is not completely formed. It does not represent a substance which can be isolated or even detected. As soon as this transition state is formed, it splits into the products. Thus, the complete reaction sequence may be represented as reactants on transition state further gives products. Energy diagrams for multi-step reactions. A reaction can proceed from reactant to product either directly in a single step known as concerted reaction, or it can take place through two or more steps which include the formation of one or more intermediates. Since the reactant is directly converted into the product without the formation of any intermediate substance is concerted reaction. The energy diagram of such reaction have only two energy minima corresponding to the reactant and the product and an energy maximum corresponding to the transition state as shown figure 3.2. Most of the reactions of organic compound are multi-step reactions involving the formation of one or more reactive intermediates. Therefore, let us now consider the complete energy diagram or multi-step reactions which help of a two-step reaction involving one reactive intermediate. Such a reaction involves formation of two transition states shown below. Reactant transition state first, reactive intermediate step 1. Reactive intermediate gives transition state 2 gives product step 2. In such reactions, we draw energy diagram for each of individual step and join them in middle at the product of step 1. Reactive intermediates act as starting material for step 2. Since intermediate has higher energy and either the reactant or products, it is very reactive and may or may not be isolated. However, unlike the transition state, intermediate has a measurable lifetime. Energy profile for a two-step reaction in which the first step is rate determining step. Then energy profile of a two-step reaction in which second step is the rate determining step. If the free energy of activation of transition state second is more than that of transition state first, energy diagram is shown 3.4. In such case, intermediate is rather stable and can be isolated. The second step of such reaction constitute the rate determining step of overall reaction. Progress of reaction. ट्रांजिशन स्टेट ए बी सी रिएक्शन की ट्रांजिशन स्टेट डी ई एफ रिएक्शन. Effect of Effect of catalyst on transition state. Many reactions which we shall study involve the use of some stable catalyst to increase the rate of reaction. What the catalyst does in reaction to provide an alternate path from reactant to product with a lower energy transition state. Thus, the catalyst lowers the energy of activation and required for reaction so that rate of reaction increases. It must be pointed out, however, that del H and del G for the reaction remains unchanged even in presence of catalyst, as any formal charge on intermediate and other ionic species. While studying the various reaction intermediates, it has been found that these species may either carry positive or negative charge, or they may be neutral in character. In order to predict whether a given species carries some charge or not, we now present a very simple method known as formal charge method for charge explanation on intermediates. Formal charge, it is amount of positive or negative charge which can be assigning to certain atom or species in order to whether the species as a whole carries some charge or not. The calculation of formal charge involves the comparison of number of valence electrons in a neutral atoms in free state and number of valence electrons associated with atom in the bonded state. The difference between the two values gives the formal charge on atoms in a given species, that is, formal charge on atom in a given species is equal to number of valence electron in free atom minus number of valence electron in bonded atoms. Calculation of number of valence electron in bonded state. The number of electrons shared between two atoms are divided equally between the two atoms and share them. This means that even though the electrons are shared between the two atoms, it is still thought as if each atom owns one electron of each shared pair. Number of non-bonding valence electrons of an atom are assigned exclusively so that the sum of numbers of electrons assigned as above gives the number of valence electron in bonded atoms. This is also sometimes referred to as average electrons, that is, number of electron in bonded atom or average electrons equal to 1 by 2 into number of shared electrons plus number of non-bonding electrons. Therefore, formal charge on a bonded atom may also be represented as formal charge on atom equal to number of valence electron in free atom minus 1 by 2 into number of shared electron plus number of non-bonding electrons. Formal charge on a species equal to sum of total formal charge on all atom in a given species. Now we illustrate the complete procedure for considering the example of simplest molecule, methane. It is apparent from the structure that carbon is surrounded by 8 electrons which are shared by 4 hydrogen atoms. Thereof number of valence electrons associated with carbon in methane is 1 by 2 into 8 equal to 4, since number of electrons in free carbon atom is 4. The methane carbon is electrically neutral. In other words, there is no formal charge on carbon atom in methane. We can also arrive the same conclusion directly. Formal charge on carbon, number of valence electron in free carbon minus 1 by 2 into number of shared electrons plus number of non-bonding electrons. Number of valence electron in free carbon atom in methane 4 minus 1 by 2 into number of shared electrons 8 plus number of non-bonding electrons 0 equal to 4 minus 4 equal to 0. Each hydrogen atom in methane is surrounded by 2 electrons which are shared with carbon. Therefore, formal charge on each hydrogen equal to 1 minus bracket 1 by 2 into 2 equal to 0. Formal charge on methane molecule, formal charge on carbon plus 4 into formal charge on each hydrogen. 4 multiplies 0 plus 0 equal to 0. It is of course well known that methane molecule has no net electrically charged free radicals. It has been stated earlier that free radicals are electrically neutral species. To justify this, let us consider methyl radical, which is simplest free radical. The carbon is surrounded by 6 bonding electrons shared with 3 hydrogen and 1 non-bonding electron. Each hydrogen is surrounded by 2 shared electrons. Therefore, formal charge on carbon 4 minus 1 by 2 into 6 plus 1 equal to 0. Formal charge on each hydrogen 1 minus 1 by 2 into 2 plus 0 equal to 0. Formal charge on methyl radical, formal charge on carbon plus formal charge on hydrogen 0 plus 3 into 0 equal to 0. Carbocations. The positive charge on carbocations may be verified by considering the case of methyl carbocation. It may be easily seen that formal charge on carbon equal to 4 minus bracket 1 by 2 into 6 equal to 1. Formal charge on each hydrogen equal to 2 minus 1 by 2 into 2 equal to 0. Formal charge on the carbocation is equal to 1 plus 3 into 0 equal to 1. Carbanions. It is well known that carbanion are negative charge species in which a carbon atom carries negative charge. To rationalize this, we may consider structure of methyl carbanion. Formal charge on carbon 4 minus bracket 1 by 2 into 6 plus 2 equal to 1 minus 1. Formal charge on each hydrogen 1 minus 1 by 2 into 2 plus 0 equal to 0. Formal charge on carbanion minus 1 plus 3 into 0 equal to minus 1. Carbene. The simplest carbene is methylene. Formal charge on carbon 4 minus 1 by 2 into 4 plus 2 equal to 0. Formal charge on each hydrogen 1 minus 1 by 2 into 2 equal to 0. Formal charge on carbene equal to 0. Carbene are neutral species. Nitrines. The neutral character of nitrines may be verified with the formal charge calculation on methyl nitrine. Formal charge on carbon 4 minus bracket 1 by 2 into 8 plus 0 equal to 0. Formal charge on nitrogen equal to 5 minus 1 by 2 into 2 plus 4 is equal to 0. Formal charge on each hydrogen equal to 1 minus 1 by 2 into 2 equal to 0. Formal charge on nitrogen equal to formal charge on carbon plus formal charge on nitrogen plus 3 into formal charge on hydrogen equal to 0 plus 0 plus 3 into 0 equal to 0. Thank you.